Last episode, we found 4 little tensor cores tucked inside every SM, and I said that is where the flops come from. Here is why. A regular CUDA core multiplies 2 numbers, a tensor core multiplies 2 whole matrices, and adds a third in a single operation. Stack a transformers matrix multiplies on top of that, and you get the speed that makes any of this possible. Picture the operation as D equals A times B plus C, 2 matrices in, multiply, add a third one shot. The clever part, the inputs can be low precision, say 8-bit, but the running total, the accumulation, is kept in full 32-bit. You get the speed of small numbers and the accuracy of big ones. That fused multiply accumulate is the entire trick. Now the precision ladder. A number format splits a budget 3 ways: range, how big it can get; precision, how many digits; and size, how many bytes. Walk down: 32 bits, 19, 16, 8, 4. Smaller is faster and cheaper to move until accuracy snaps. The most important rung to understand is the two 16-bit formats. FP16 spends its bits on precision but has a narrow range, so big activations overflow. BFS16 keeps the full 32-bit exponent, same range as FP32, and just gives up some precision. That is why modern training is BF16, no overflow, no fiddly loss scaling. Before you even drop precision, you can shrink the model itself. Knowledge distillation. Take a big accurate teacher model and train a small student to copy not just its final answer, but its full softened probability distribution, the so-called dark knowledge in how confident it is across all the wrong answers too. Soften the teacher with a temperature, let the student match it, and you get a small model punching above its size. Distill. BERT did this. NVIDIA's Minitron does it for modern LLMs. Pruning is the cousin, just delete weights you do not need. And the hardware has a pruning trick built in, 2 to 4 structured sparsity. Force the model so that in every group of 4 weights, 2 are 0. The sparse tensor core then skips those 2 and roughly doubles throughput. The catch is the word structured. Random unstructured sparsity saves storage, but the hardware cannot exploit it. There is no fixed pattern to skip, so you get no speed up. That is why datasheets print 2 numbers, dense and with sparsity. Always read the dense one as the honest one. And the eras matter. FP8 starts at Hopper and Ada. The A100 does not have it. FP4 is Blackwell only. Let me put the whole ladder on one chart because the shape of it explains the last 6 years of AI hardware. Bits on the x-axis, relative speed on the y. Watch what happens as the bits fall. Start at FP32, 32 bits, speed 1, the reference. Every step down the ladder roughly doubles the throughput. TF32, FP16 and BF16 at 16 bits, FP8 at 8, FP4 at 4, half the bits above double the speed. That is the engine behind bigger, cheaper, faster every single year. Now I will color each bar by its dynamic range and split the two 16-bit formats apart. FP16 and BF16 are the same length, same 2 bytes, but BF16's range bar matches FP32's, while FP16's is short. Same size, very different safety. This is the single most useful slide in the stage. Overlay the error line. Volta brought FP16, Turing INT8, Ampere added TF32 and BF16 and 2 to 4 sparsity. Hopper and Ada brought FP8, Blackwell brings FP4. The ladder is not abstract, each rung shipped in a specific chip, and I will draw the sparsity bonus as a faint double bar on the formats that support it, labeled with sparsity illustrative. Half the bits double the speed all the way down to 4, but there is a number this chart does not show. How much memory the model and its growing conversation actually eat, and whether they fit on the card at all. Speed is useless if it does not fit. Next, sizing a real deployment. Weights, the KV cache. and why decode is bandwidth bound. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.